My name is David Stevenson, as you can see there, writ large. And what I'm going to be talking about today is introducing AI into print workflows. So a year ago, I gave a presentation at this conference titled, and I have to read this, Intelligently Estimate, Optimize and Tune for Variable Data for Production Efficiency. Very catchy title. And in that, I laid out the case for ripping directly to printhead electronics on an inkjet roll-to-roll press. And that leads to a need to correctly identify when a job is going to be able to be ripped fast enough to keep up with the desired press line speed. I then went on to talk about some of the innovations that Global Graphics were working on in that area. Well, a year on, we find ourselves with a patent granted on this application of AI, and we've also delivered products to some of our OEM customers who are using them in production today. So I can talk in a little bit more detail now about exactly what we did. So just restating the problem, the challenge is that inkjet opens up the opportunity to print with every page different. So you can have highly personalized content being printed. The resolution and size of the presses, of inkjet presses, is increasing all the time. Single pass line speeds up to 300 meters per minute. And we also see that being used in the manufacturing space for things like printing tiles, carpets, flooring, that type of thing. There's a drive towards using extended gamut. So using additional inks on the inkjet bar to provide a greater color gamut. But that means more channels that have got to be processed by the RIP to generate the rasters for that particular channel. And also improvements in screening as well demand more processing. So the challenge then is to figure out can the job run fast enough. But first of all, I would just take a moment just to talk you through what Smart DFE is all about, and then I'll focus in on smart performance. So this is the Smart DFE offering from Global Graphics, and we start out with the workflow, which is where jobs come in. VDP is expanded, the job is pre-flighted, imposition is handled to suit the particular output format that's required. And then the smart performance bit, and I'm the product manager for this bit, so there's a bit that I'm interested in, and I'll be talking more about in a moment. This is where we use this AI-based approach, but it's about analysing the job and then recommending some settings for the RIP to suit that particular job, and also potentially certainly to estimate it, how fast is it going to run, and potentially also to optimize it. So we have some capability to optimize jobs. We don't always need to do that, but if that's required to make the job run fast enough, then that's what we'll do. Smart control is where we actually send the job to the RIP, and that's concerned with queuing the job and actually driving the RIPs that are over on the right-hand side there, that are then driving rasters to the printhead electronics. Probably our sister company Meteor will be providing those, but we can obviously work with any. And then driving the inkjet bar itself. And that can be distributed across a number of PC devices, so we can have a separate PC for each color channel, that type of thing, to improve performance. Smart quality is where another of the hybrid sister companies comes in, a company called Color Logic, and that's really concerned with ensuring the color fidelity of the job. It also talks to some capability we have to generate rasters which are compatible, so in a way that allows those page rasters to be compared to a camera image that is being used to monitor the jobs coming through. So it can do a direct comparison between the two. And then finally, the smart connectivity over here. So one of the things we've built into the system is something called APC, which is actually a factory communications protocol. So it's really speaking to the capability of Smart DFE to sit in a manufacturing setting, which some of our customers want to do, but it also gives us the ability to reach out to MIS systems and to other systems that the customer may want to integrate with. We also use that OPC capability as well to control components within the system. So let's talk a little bit more about smart performance and where the AI bit comes in. So the idea is, and I repeat myself here for some reason, I don't know why, but every job is analysed and estimated. And simply put, we have some technology at Global Graphics called Mako, which is an SDK for print workflows. And we use that to examine the PDF job, actually look at every single object on every single page, and infer some information from it. So we use it to generate a little thumbnail, which you can see there. And then from the operator's point of view, all they see is this traffic light. One of those jobs is red, another one is green. And what that actually refers to is this print speed indicator. This is another setting in one of the settings in the thing in Smart DFE, where you can control the target line speed for the press that you happen to be using, and then you can control the safety zone as well. The idea is that this traffic light system gives a very easy indicator to the operator: can I run this job safely at the line speed that I want? And the question then is, how do we work out that estimation? How do we know how fast the rip is going to go? So the way we do it is, this is where the AI bit comes in. And AI seems to be mot du jour at the moment. So I thought I'd talk about it in a little bit more detail. We're actually using what's known as machine learning, a neural network that allows us to well, first of all, we start out with generating thousands of data points, and I'll go into a bit more detail in a second about where those data points come from. And then we use a neural network to generate weights. Each of those measure the contribution of a given operation that the RIP would have to perform in order to composite or render or rasterize that particular part of the page. And then we train the model. We run thousands of runs to gradually tweak those weights so that when we have the different combinations of objects on the page, that they accurately reflect the contribution that particular element on the page would make to the ripping process. And when we first were working on this, it was taking something like 26 hours to train the model. We've got it down now to a few hours, but it's still a very time-consuming process. The thing is that once you have that model, then it's very, very, very easy and very quick to actually analyze novel data, a new PDF, a job that's come into the system, and to estimate the time it's going to take to rip. How do we generate that data? Well, we have, and I had to look this up. We model 213 operations, and in around 10,000 distinct combinations. So this will be, vectors, images in different orientations, different compositing requirements. The different colours, all the different colour spaces that PDF supports, We've got to look at the transparency, so where transparency is required. And what's interesting about this, or it was for us anyway, when we were modelling the RIP behaviour, was we sort of rediscovered how the RIP worked. I keep talking about the RIP. The RIP is the Global Graphics Harlequin RIP, which we use in the Smart DFE. And it's been around for a while. You know, the company started more than 30 years ago. And so there are lots of different code paths that a job can take through the RIP. And so we have to use AI really to do this modelling. There isn't any other way to do it. But we found it to be very effective. And what's good about it, well, I'll come on to a little bit more about that. So what have we got here? This graph here is each of these jobs, each of these dots rather, represents a job, a PDF job. And on the x-axis, we've got the actual time it takes to RIP. And up the y-axis, we've got the predicted time. So using that model to predict the RIP time. And obviously what you want is you want everything to be on that nice center line that indicates that the predicted time is equal to the actual time. And in particular, you want to try and avoid underestimating. Overestimating is okay. Underestimating, not so good. But you can see a lot of the jobs, particularly some of the smaller ones, which take very little time to do, and there's very good convergence there. Over here we have a graph that we actually make this available in the product as something we call the fingerprint report. Each of these is a page. The bars represents all of the operations, a sum of all of the operations that are needed to RIP that page. And the different colours actually refer to different operations that are needed to actually do the ripping. And you'll notice that it varies wildly across the job. This is because this is actually a sort of although this is a personalised job, it's what we call a multi. I've forgotten the name of it now. It's on my slide somewhere. But the point about it is that each page is different, so we get different RIP times for those different pages, and you can begin to see a pattern because there's a set of pages. It would be something like a utility bill with a personalised front page, and then maybe some personalised marketing material that comes after it, and it's the same thing over and over again. So in this case, a set of 6 pages. Anyway, this kind of information could be useful to an operator. It's certainly been useful for us to be able to measure the effectiveness of what we're doing. One of the things that we learned a whole lot about the behaviour of our own product, our Harlequin RIP, which was quite interesting. One of the things we did find was that it was really important for us to use the same hardware, the same PC that the RIP is eventually going to run on, because a RIP is a complex piece of software. It uses memory in a particular way, and depending on the exact architecture of the PC, which generation of Intel processor it is, whether it has fast memory and fast caches and all the rest of it, that really changes the way that the RIP can behave. We haven't found an easy way of scaling our model to suit different hardware. So at the moment we're using identical hardware to the PCs that the RIP will eventually run on. One of the things that we encountered were a lot of sort of outlier results. So this would be a job that we expected to go slow, went really quick, and another job that we expect would be really quick was really slow. And those are the ones that could catch you out in a production environment. and exactly why we've built this auto-tune system to detect that and to prevent those situations, and also to provide the mitigation. The auto-tune actually will tune the RIP. It will send RIP settings with the job to ensure that job is going to run correctly. And then my boss said, "Oh, you've got to mention Colossus." And I said, "Well, okay. Well, it is kind of important." So one of the things we do, I talked about the fact that the training can take hours. So what we typically do is we run tests continually, and we do tweaks to the model to see whether we can get the improvements in the estimation. And this collection of PCs that run all this stuff we refer to as Colossus, essentially a rack of PCs running jobs, and then using OPC, that protocol that I talked about earlier, to report results to a dashboard via OPC. In fact, we have a TV like that one up there in our office with all of the Colossus results, so that we can see how things are progressing. So that is Smart DFA. So thank you very much.
That is that. Thank you very much.